Hello, and welcome to our video covering section 8.2 of your textbook. In this video, we will discuss quadratic forms. We'll talk about diagonalizing quadratic forms, whatever that means, and then we will end with a discussion of principal axes and something known as the principal axis theorem. All right, first let's begin with some observations. Suppose we have some function with inputs x1 and x2, and it's a quadratic function of x1 and x2. So 8x1 squared minus 4x1 x2 plus 5x2 squared. This is a function from R2 to R. So something you would have seen in like Calc 3. Now, because we're in linear algebra, let's think of this, we'll think of x1, x2, this pair as a vector. And then we can think of now q as being a function where the input is a vector and the output is a scalar. Now, let's be clear. Q is not a linear function of this vector. I mean, we've got these squareds here, so definitely not a linear function. But consider these calculations. So this is our function, and now what we're going to do is we're going to break this up into two equal parts. So this is just 8x1 squared minus 2x1 x2 minus 2x1 x2 again, plus 5x2 squared. Okay, whatever. Well, sure, we can do that. Now I'm actually going to factor out an x1 from these first two terms and then factor out an x2 from these second two terms, like so. And hopefully you've been in this class long enough to think that this looks like a dot product. And in fact it is. You take some vector x1, x2, dot it with 8x1 minus 2x, and minus 2x1 plus 5x2. And there you go. That definitely is this dot product. But then again, hopefully you've been in this class long enough, you're like, ooh, that looks like a matrix times a vector. And indeed it is. And not just any old matrix. That is definitely a symmetric matrix. And that's by design. And this is why I broke this in half, and so that I could have equal coefficients here. But okay. And so really we've taken this function q of x and we've written it in this form x dotted with a of x. Or your book really enjoys writing this also as x transpose times a of x, but that's fine. They're the same thing. And key is that the matrix A is symmetric. So, okay, we were able to do that with this quadratic form. Let's consider a more complicated function. So now a function from x1, x2, x3 to r. And so in this function, we've got, I guess I put the squared terms out front. So we've got 9x1 squared plus 7x2 squared plus 3x3 squared. And then we've got our mixed terms, minus 2x1 x2 plus 4x1 x3 minus 6x2 x3. So all the possible combinations of x1 and or xi and xj are captured here. And let's try to do something similar. So these are our mixed terms. We'll break up each mixed term into two parts. So 2x1 x2 gets 2, or minus 2 x1 x2 is minus 1 x1 x2 minus 1 x1 x2. Similarly, the 4x1 x3 gets broken up into two 2's, and then minus 6 x2 x3 gets broken up into two negative 3's. All right, and then factor out an x1 from the 9x1 squared minus 1 x1 x2 plus 2 x1 x3. And similarly, you factor out an x2 from the next three terms, and or the appropriate three terms, and similarly for the x3. And now we're off to the races. This looks like a dot product. And you like pull out the dot product, and then you're like, oh, that looks like a matrix product, and it definitely is. And because we've separated all of these cross terms equally, we are going to get another symmetric matrix. So once again, we can write this quadratic form in the form x dot ax or x transpose times ax, whatever you prefer, where this matrix A is symmetric. All right, so this leads us to a definition and a theorem all in one. So first, we have a definition. I think I said the word quadratic form earlier without actually defining it. So let's define it. Quadratic function from x1 to xn, or yeah. So a quadratic function from Rn to R was called a quadratic form. A function is called a quadratic form if it is a linear combination of functions of the form xi, xj, where I and j might be equal and run through 1 to n. So it's something that looks like this, where you've got, all right, some coefficient on x1 squared, a coefficient on x1, x2. You'll have some x2 squareds in there. You'll just get all the possible mixed terms, xi, xj, all the possible pure squared terms, xi squared, xj squared, all the way down to xn squared. And I just put the subscripts on the coefficients to keep track of, what the terms are. So b11 just means it's two x1 terms. The ij means you have xi times xj. So anyway, this is like the general kind of quadratic form. And then your book includes in the definition something that is totally a theorem, which is that any quadratic form can in fact be written in the form x dot ax or x transpose ax for a unique symmetric matrix A. And so this is what we were doing. We were constructing this in the previous two examples. And I'm not going to, I guess, not prove this, but I'll just say, like, here's how you construct it in general, and then convince yourself that, yeah, this is right. This theorem is true. So the entries, I claim, of the symmetric matrix are going to be as follows. So along the diagonal, so your AII in your matrix A, just make that the entry BII. So make it the coefficient of the pure squared terms. And then all the other terms, like the B12 and the BIJ, split them in half. And then, split it in half. And then make one of those the IAJ term and the other one the IJI entry for, whenever I is not equal to j. So mixed terms, split them in half and put them in corresponding places in your matrix so that your matrix is symmetric. And if you do this, then yes, you will have written your quadratic form in the form x dot ax. Now, the fact that A is symmetric should totally make you think spectral theorem. Like, you should be thinking orthonormal eigenbases, diagonalization. What happens? Like, you should be thinking, okay, what happens if A is symmetric? Well, we've got orthonormal eigenbases. So what if I wrote X in terms of the eigenvectors? So let's see what happens when we do that. This is, what's known as diagonalizing quadratic forms. So let's go back to this first example where we wrote q of x in this form. You can check yourself that the eigenvalues of this matrix A are going to be 9 and 4, and that the associated eigenvectors, orthonormal eigenvectors, will be, these are normalized, 1 over root 5, 2, minus 1, and 1 over root 5, 1, 2. Okay. Now, let's see what happens when we write x in terms of our orthonormal eigenbasis. So C1 and C2 are the coordinates of x in the basis V1, V2. Then what's going on? Well, let's calculate x dot ax. So x is C1, V1 plus C2, V2. And then A, C1, V1 plus C2, V2. And now, because these are eigenvectors, we can write this as C1 lambda 1 V1 plus C2 lambda 2 V2. And then, okay, we're going to have to FOIL this out, but the cross terms are all going to go away, you'll see, because V1 dot V2 is going to be 0 because these are orthogonal vectors. So yeah, multiply this all out, you get this business. You can check to see if I have any typos or not. But note that the term with V1 dot V1, well, because these are normal vectors, they're length 1, V1 dot V1 is going to be 1. V1 dot V2, because V1 and V2 are orthogonal, 0. this is also going to be 0. b2 dot b2 also going to be 1. So we end up with c1 squared times lambda 1 plus c2 squared times lambda 2. And then we know what lambda 1 and lambda 2 are, so let's write it out. So okay, we have now rewritten our quadratic form. Instead of having mixed terms, this mixed term here, we've essentially completed the square, and we have a pure squared terms here. Yeah, so we've got a quadratic equation now with no cross terms. And these are just, instead of up here, we've got x1 is like the coordinate on your x-axis, and x2 is your coordinate on your y-axis. Now we've got c1 is the coordinate on our axis through v1, and c2 is the coordinate on our axis through v2. But yeah, we've got just a normal quadratic equation with no cross terms. And in this form, the behavior of the quadratic form is easy to understand. Like, we can kind of see right away, well, all right, q of x is going to be 0 if x equals 0 and positive otherwise. And why is that true? Well, if we have x be the 0 vector, then, all right, c1 and c2 both have to be 0. And so 9c1 squared plus 4c2 squared, got to be 0. What if x is non-zero? Well, if x is non-zero, then at least one of these coefficients, c1 or c2, has to be non-zero. But then if you go down here, one of these is non-zero, then this whole term has to be non-zero, and since the coordinates are squared, it's going to be positive. So there you go. This motivates this following theorem. It's called diagonalizing a quadratic form. So it says, all right, suppose you have a quadratic form, it can be written in this way, where A is a symmetric matrix, and now let pretentious B be an orthonormal eigenbasis for A, which is guaranteed by the spectral theorem, and it has associated eigenvalues lambda 1 through lambda n. Then we can write the quadratic form in this way, where q of x is lambda 1 c1 squared plus lambda 2 c2 squared all the way to lambda n cn squared, where the c1, c2 all the way to cn, these are the coordinates of x with respect to the orthonormal eigenbasis for A. And so the whole point of diagonalizing a quadratic form is to get rid of these mixed terms so that we can better analyze our function. And the most basic analysis you can do is just to decide whether the function always has the same sign, like whether the function values have the same sign. For example, like we just saw previously, this quadratic function, we say, all right, well, it's positive everywhere that's non-zero. So that's some basic analysis you can do. It turns out this analysis is something one likes to do quite a bit, and so we have terms for this. We call it the definiteness of a quadratic form. Man, that looks like it should be definiteness or something. I don't know. For whatever reason, I'm reading that. I'm like, that doesn't look right. When I said it, it doesn't sound right either. Anyhow, consider a quadratic form. Looks like this, where A is a symmetric matrix. We say that A is positive definite if Q of X is positive for all non-zero X. So, all right, X equals 0, you're always going to have a 0. Your quadratic form is always going to be 0. But if X is non-zero and the quadratic form is always positive, then we say the matrix A is positive definite. A is positive semi-definite if Q of X is greater than or equal to 0 for all X. So this is really implying that there's some non-zero X that might also send you to 0, but then otherwise you are going to be positive. And then similarly, you can define negative definite and negative semi-definite. And then we'll say matrix is indefinite if its quadratic form takes positive as well as negative values. So first, I just want to note that so every symmetric matrix A corresponds to a quadratic form. And definiteness is a property of the matrix. But it's determined by the values of the quadratic form. So that's just something to keep in mind. Definiteness is the property of the matrix, but you determine definiteness by looking at the quadratic form. But this kind of makes sense because we have this like one-to-one correspondence between quadratic forms and symmetric matrices. So, okay. And now we have this theorem that says a symmetric matrix A is positive definite if and only if all of its eigenvalues are positive. And it's positive semi-definite if and only if all of its eigenvalues are either positive or zero. And this just comes from the previous theorem that told us we can write the quadratic form in this way. And so if we can see immediately if all of the eigenvalues are positive, well then all the coordinates are going to be non-negative. And so if x is non-zero, one of these coordinates is going to be non-zero. And so your quadratic form is going to be positive definite if all the eigenvalues are positive. And positive semi-definite, well, if one of these eigenvalues is zero, then you can have you can let your coordinate attached to that be non-zero and everything else be zero, and it'll be your function will be zero for some non-zero x, but it's never going to be negative. And if you're wondering, there is like a corresponding theorem for negative definite and negative semi-definite, which we're not going to bother to state. So, okay, we are most of the way done. Now we're time to talk about principal axes. So let's go back again to that first example. So here, converting this quadratic form to the like pure squared form, 9c1 squared plus 4c2 squared, what does this tell us? This actually tells us that q of x, this quadratic form, is an elliptic paraboloid oriented along the axes through these eigenvectors. So kind of like I was saying earlier, like if you just think of x1 and x2 as the coordinates on the x1, x2 axes, then think of c1 and c2 as coordinates on the c1 and c2 axes. And these axes are going to be the eigenspaces through eigenvectors v1 and v2, and they are orthogonal to each other. So these are like a perfectly good set of axes to work with. And this is just the equation for an elliptic paraboloid, that you would see in your Calc 3 textbook. So you've got your x1, x2 axes, and now we've got this alternate set of axes, the v1, I guess maybe I'll call them c1, c2 axes. And if you plot, so this, I put this in GeoGebra, but it should be no surprise that you get your elliptic paraboloid is oriented along these axes. So, I think that's pretty cool. And these axes, the axes through the eigenspaces, these are known as the principal axes of the quadratic form. And I don't know, makes sense to me why you would refer to these as the principal axes. So let's do another example. So you have this quadratic form we haven't seen before. You can check that we can rewrite it with this symmetric matrix. You can also check that the eigenvalues of this matrix are 9 and -8 and has the associated orthonormal eigenvectors v1 and v2 that look like this. And so when you diagonalizing this quadratic form, we would get 9c1 squared minus 8c2 squared. And this, if you remember from Calc 3, is a hyperbolic paraboloid. But now, instead of oriented along the xy axes, it's oriented along the axes through the eigenspaces corresponding to v1 and v2. So looks something like that, in case you forgot what a hyperbolic paraboloid was. And this is like a top-down view, so you can see that, yes, these axes really are like the perpendicular axes that the hyperbolic paraboloid is oriented along. I guess one thing I'll say before moving on is that your book gets really excited about like cross sections of this. So they're like, whoa, what happens when the quadratic form, you take this and set it equal to 1? Well, okay, that's just taking a cross section that's going to give you hyperbolas. And similarly on the last one, you get a cross section that gives you an ellipse. And I think your book like breaks this out into a theorem or something, and I'm not going to bother to do that. But I'm just acknowledging that your book does do that, and I'm not going to. Okay, so let's really have a solid definition of principal axes. I like kind of hand wavy mentioned them earlier. So if you have a quadratic form, it can be written in this way. And suppose that the symmetric matrix has n distinct eigenvalues. So these are all different. In this case, the eigenspaces of A are all called the principal axes of the quadratic form. And if you have n distinct eigenvalues, then okay, these eigenspaces will all be one-dimensional. So it's very clear each eigenspace would just correspond to its own axis. And now I'm going to talk about the principal axis theorem. So recall, a quadratic form, written in general, can be written like any general quadratic form can be written like so for symmetric matrix A. This was the theorem part of the secret theorem in the definition 8.2.1. And then recall that any quadratic form can be written like so. This was the diagonalizing a quadratic form theorem. These facts together are sometimes referred to as the principal axis theorem or principal axes theorem. I've seen it both ways in sources that I respect. So so you might see it either way. So sorry if I got you all excited about like, ooh, a new theorem. No, it's just like theorems that we've seen before. Like sometimes this stuff gets called the principal axis theorem. And someone on Wikipedia said that the principal axis theorem is just the geometrical counterpart of the spectral theorem. And that was, anybody could say anything on Wikipedia, but the math pages are usually pretty good. And this does make a lot of sense to me. And I also vaguely remember reading something like this in Gilbert Strang's book. So, and like that guy I definitely trust. But yeah, I think this kind of makes sense. Especially if you think about it, okay, symmetric matrices and quadratic forms, they've got this one-to-one relationship. Spectral theorem says symmetric matrices have an orthonormal eigenbasis. And the principal axis theorem says the quadratic form has an orthonormal set of axes, which are the eigenspaces. Yeah, it has an orthonormal set of axes where the quadratic form can be pure squares. So I don't know. I see it. I see it being like just the geometric version of the spectral theorem, which is pretty cool. And it seems like a nice place to end on.